Here's the second max-min example problem. This time you're given the graph of y equals 4 minus x squared, specifically between x values of 0 and 2, and you're creating a cone that fits into that graph, that's bounded by that graph. And the idea is that you want to find the maximum volume of a cone. So basically, as you make it taller, you can see that the radius is going to have to be smaller. As you make it shorter, you can see that the height will be lower, but the radius will be bigger. And so the question is, where along there is your perfectly dimensioned cone going to take place that gives you the maximum value? So let's take a look at that.
So, to try to figure out what we're doing with this cone problem, I've started out by drawing a diagram, okay? As always, you always want to make sure you have a really good, well-labeled diagram. Number two, you want to come up with some kind of equation that you're going to maximize or minimize. And you also want to do something having to do with the constraints. I'm actually going to wait a little bit on the constraints. We want to maximize the volume, okay? In many of these cases, whatever you're going to maximize or minimize is going to tie into some nice geometric formula, that kind of thing. Volume of a cone, of course, is 1/3 the area of the base times the height when it comes to a point like that, which, of course, is going to be 1/3 area of the base would be pi r squared, and then h. I want to write this function in basically using the variables for a regular graph, okay? So I'm going to do this as functions of x and y. And so specifically, this is where the constraints are going to come into play. They kind of go hand in hand with the diagram in many cases, and this is one of them. So if I draw my radius in here, that radius value is going to be the point x comma y. Okay, as we move this around on here, that point changes. I don't know what either the x or the y coordinate is. And keep in mind, I can also use that then to determine the height of this thing. The height is actually just going to be y. So I can go to this formula over here and I can fill those values in using what I have on the graph. The radius is x. Okay, so that's going to be x squared. I want to put that in parentheses. And then the height is going to be y. So in a sense, I can use the formula volume equals 1/3 pi x squared y, but I don't want to have my function written in terms only of, well, I don't want it written in terms of two different variables. Okay, here's where the constraints come back into play. I was actually given the constraints equation when I was given the original function. Okay, I didn't maybe realize it. But if you think about it, this function is a constraint. I can't have any sized cone that I want. It's got to fit under this graph. So the constraint is basically that y has to equal 4 minus x squared. That's this green function here. And then I can do my maximizing and minimizing. So if you remember from the previous example, when I write my function in terms of one variable, in a lot of cases I can use that constraints equation to eliminate one of the variables. Okay, so you can see here that's the information that I have. So I am going to replace the y in the function with the 4 minus x squared. So the volume in terms of one variable is going to be 1/3 pi times x squared. Actually, I won't put the parentheses there. I'm just going to square x times that y value of 4 minus x squared. And then basically at this point, I might want to do a little simplifying. Volume is equal to 1/3 pi, that'll be times 4x squared. Actually, we'll multiply all of that times 4. So that'll be 4/3 pi x squared, be a little better way to write that. Now I'm going to take the 1/3 pi x squared and multiply it by that. So it'll be minus 1/3 pi x to the 4th. Okay? Now, where do you go from this? Well, I need to find the maximum or minimum value. And if you graph this, I don't remember exactly what the graph looks like, but it basically does something kind of like this. You'll notice here, this is not your standard quadratic. We've got an x to the 4th. But anyway, there's going to be a point here that is the maximum value. And the thing that is so important to remember here is calculus allows you to find a maximum or minimum when the derivative is equal to 0. And so you can see right here, if we can figure out where that derivative is equal to 0, we're good to go. Okay, so I will find my derivative equation. The derivative in this case is going to be 8 v prime equals, it'll be 8/3 pi x minus 4/3 pi x cubed. I want it to equal 0, so I've set it equal to 0. This, of course, is the v prime equation here. And I can do some factoring, okay? I can factor out a 4 and a 3, 4/3. And I can factor out a pi, and I can factor out an x. And that's going to leave me with 2 minus, let's see, take out an x. Looks like it's going to be 2 minus x. Wait, I took out one x there. I'm sorry. It's 2 minus x squared. Okay, so either this part of the product can be 0, and that would be x equals 0, or this part can be 0. If I needed 2 minus x squared to be 0, x would basically be the square root of 2. Okay, negative square root of 2 would be outside of my domain here. So that's basically the key, and that's where this problem ends. If you wanted to finish this, you could substitute this back in. Basically what we found out is at an x value of radical 2, you're going to get the maximum volume cylinder. And of course you could stick that back in here. That's going to be, in this case, radical 2 squared will just be 2. And let's see, the height, well, the height is y. The y value is equal to 4 minus the x value squared. So that's radical 2 squared. Radical 2 squared is 2, so that would be a y value of 2. And so we'll have a height of 2. And so your maximum volume in the end will be 1/3 pi times 2 times the height of 2 squared, which is going to be 4. And that's going to end up being 8/3 pi cubic units in the end. So again, look at the problem. Sometimes they ask you for the maximum, or the dimensions that result in the maximum volume. Sometimes they ask you for the multiple maximum value, and sometimes they just ask you for any one of those. But that's the main idea. So same kind of thing as before. Get a diagram. In this case, we were given a constraint equation, but if you're not given one, then you've got to write one. Usually then you're going to use that constraint equation to substitute into your function for maximizing or minimizing and write it in terms of one variable. And then the maximum minimum value takes place where the derivative is 0. So if you get that little series of steps down, really the key is going to be writing those equations. The hard work in most of these problems, strangely enough, is going to be algebra.